Hello ChemComm. Today we're going to look at the last equation of gas laws, which let us know how many moles of gas we have based on the pressure, volume, and temperature. Let's get started. Today we're going to talk about the ideal gas law. The ideal gas law requires us to assume that we're dealing with a gas that is ideal. An ideal gas should be behaving according to the kinetic molecular theory, but there are certain cases when this does not take place. For instance, if you have extremely high pressure or extremely low temperature. With an extremely low temperature, the particles are going to start moving very, very slowly. And this disrupts intermolecular forces and causes the gas to not behave according to ideal conditions. In the same way, if you have extremely high pressures, the molecules are going to be very, very close together, and this may cause condensation into a liquid, which would disrupt the ideal gas behavior. What this means is that in most cases, this equation does work correctly, but in certain circumstances, the math would not model reality if you have extremely low temperatures or extremely high pressures. When Avogadro did his initial experiments, he did them with gases, and he theorized that equal volumes of different gases would have the same number of particles, 6.02 times 10 to the 23rd. That's how he came up with the number 6.02 times 10 to the 23rd for 1 mole of gas. He also discovered that a mole of gas would equal a specific amount of volume, which is 22.4 liters. So we know that 1 mole of any substance equals 6.02 times 10 to the 23rd particles. We know that 1 mole of any substance equals the molar mass of that substance. And now we know that 1 mole of any gas will equal 22.4 liters of volume. Because we know gases take up the same volume no matter what gases they are, we can use this in a stoichiometry equation to determine how many moles of any gas we would produce. So if you look here at this problem, we have 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of water vapor. This wants us to know how much water vapor will produce from 3.5 liters of O2. We can go from liters of O2 directly to liters of water because we know that 1 mole of each will take up 22.4 liters. So we'd put liters of oxygen on the bottom, and we put liters of H2O on the top. And then we just use our mole ratio. So the liters of oxygen is just 1 because there's 1 mole of O2 in this equation. And the liters of H2O is 2 because it has a coefficient of 2 in front of H2O. We would take 3.5 and multiply it by 2, and that would mean that we would produce 7 liters of H2O. This simplifies the problem because we don't have to go from liters to moles, then moles to liters. We know that a mole of any gas is 22.4, so we can use the coefficients as a direct conversion. All right, let's move on to the ideal gas law. This equation basically gives us general relationships based on the other gas laws that we've developed. But now we can integrate Avogadro's information to show an amount, or how many moles of gas we have. Notice that this equation has some of the familiar variables, pressure, volume, temperature, which is in Kelvin, but we also have N, which is the number of moles of the gas, and then we have R, which is a constant. That constant will always be 0.0821. Notice the units on the constant are atmospheres, liters, moles, and Kelvin, which means that your pressure has got to be in atmospheres, your volume has got to be in liters, moles, and you have got to be in Kelvin. You can't use the constant 0.0821 if your pressure is in kilopascals because that constant is for atmospheres. All right, so let's do a problem. This says we have 2 moles of hydrogen. That variable is N, and we're at 40 degrees Celsius. We would have to convert that into Kelvin. 40 plus 273 would equal 313. And so that becomes our temperature. And then we have 50 atmospheres. The second you see that we have moles in this problem, you should be thinking PV equals nRT. A lot of times this equation is referred to as PVnRT because if you sound it out phonetically, it sounds like PVnRT. So pressure was 50 atmospheres. Volume is what we're looking for. The number of moles is 2. And the temperature is 313. Notice it doesn't say anything about R, but if you are doing a PVnRT equation, R is always 0.0821. At this point, we're going to divide both sides by 50 so that it cancels out on the left, and we're just going to calculate our volume. This gives us a volume of 1.03, and that has got to be liters because our R value is in liters. This next problem is a little more complicated. Notice that it doesn't include a lot of numbers. The first thing it gives us is grams of carbon monoxide. We need to convert this to moles so we can put it in our PVnRT equation. So grams of CO goes down here, and moles of CO goes up top. 1 mole of any substance equals the molar mass of that substance. So we take 1 carbon and 1 oxygen, that gives us 28 grams per mole. 88 divided by 28 equals 3.14, and that will be moles of CO. And that is our N value. Now we have to deal with STP. So let's write out PVnRT. Standard pressure is 1 atmosphere. We do not know volume. We just calculated our number of moles to be 3.14. R is always 0.0821. And standard temperature is 0 degrees Celsius, which is 273 Kelvin. We would divide both sides by 1, which obviously is easy to cancel out. And we'd get a volume of 70.4 liters. So that problem's a little more involved, and you have to remember what STP stands for and what those numbers are. But after you get the problem set up, it's pretty straightforward. PVnRT is definitely adding in some other variables. Make sure you always remember to put the R constant in. And also, anytime you see moles in the word problem, you know that it's going to be a PVnRT problem. Keep practicing. We'll see you soon.